Welcome. So this is our second video. This is 48I video 2, and now we're going to look at the situation when we have forces that are not constant. They actually vary as the position of the object that the force is acting on varies. We're going to make a concession, and rather than having the direction of the force and the displacement change, we're going to keep them parallel to each other. So we'll have a force and we'll have a displacement that are parallel to each other, but as the displacement passes, the force may get bigger and may get smaller, etc. We'll always keep the force and the displacement parallel to each other. We say this is the work done by a varying force, and this is a slide using graphs. We say consider the work done by the force that varies with displacement. Remind ourselves the work done by a force is equal to the area under the graph. So first of all, the first mistake is people go to the bottom of the graph. Well, I have negative forces in here. I have forces in the other direction. So we go to the axis. And secondly, sometimes don't ask for the whole displacement. So I might say, what's the first done between 0 and 2 meters? Or I might say, what's the work done between 0 and 4 meters? Or I could say, what's the work done between 2 and 6 meters? So you got to watch out and see what the question's asking. This says, what is the work done by the varying force during this 6-meter journey? It's a given that these two guys are parallel, so I don't have to worry about the angle between them. And so it's the area under the curve. And so I say, oh, well, this is my first recognizable section. It looks like a square. Do not count squares. It's actually a rectangle. It's 1 unit high and 2 meters wide. So it's 2 times 1, the base times the height. And then this yellow section here is a triangle. I can recognize it as such. And it's a half the base times the height, which is a half of 2 times 2. And then this next section here is also a triangle, and this is a half of 2 times 1. And then the final section here is this grey area, and that is a base of 2 times a height of 2, which is a base of 4 times a height of 2, which is 4 times 2. And so 2 ones are 2, a half of 2 times 2 is 2, a half of 2 times 1 is 1, and 4 times 2 is 8, 8, 9, 10, 11, 12, 13. My work done is 13 joules. Sometimes I find people counting squares. That only works if the two axes have the same scale, and usually in physics and engineering they don't. So it's not a hard question, it's just that you've got to practice it. So in this next slide we have a varying function. It varies so smoothly we can represent it by an equation, and we say this is the work done by varying a force, and we're going to use calculus. We're going to say consider the work done by the force that varies with displacement. The work done by the force is equal to the area under the graph. Again, we're assuming the force is parallel to the displacement. And we're going to call the displacement delta x. That's just traditional at this point. And we say, well, the work done is equal to the area under the graph. We'd say that the little bit of work done in this slice is equal to my delta x times my force of this slice, and then I have a whole bunch of slices to add together, and so I say the total work done is equal to the summation of all these slices, the fx times the dx. This is my fx. And so in the limit, as these slices get thinner and thinner, I have the integral of fx dx. Notice this x here is a subscript. It's telling you that it's the force at this position basically, and dx is basically an incremental width. They're completely different things. Sometimes with poor handwriting it becomes fx dx, and then the next thing you know is when you're trying to go through your notes you can't remember. You can't interpret it clearly. So be careful with your presentation if you can. Just tighten up a little bit and it will pay dividends. So the next thing we do is, until we recognize that this is the work is equal to the integral of fx dx. Cool. Let's look at some examples. It says, what is the work done by varying force during the first 8 meters of this journey? So let's put a line there so that that's where we stop. And we go to the 0. So let's put a line there. Okay. So we have, let's have a look. We have a triangle. We have a rectangle, a triangle, and a triangle. I have 4 areas that I need to take into account. I can forget this thing beyond 8 meters. I have 4 bits. I have 1 bit. I have 2nd bit. I have 3rd bit. And then I have this 4th bit. So let's see if I can keep those colors. What's my basic equation? So the work is equal to, what can we say? It's actually the integral of fx dx, which equals area under graph. Under meaning to the origin. So work is equal to, let's see if I can get the colors the same. It's going to be a half of 2, there's 2, times 10, because it's a triangle. And let's add that to the next section, which is this rectangle, which is the base, which is another 2, times the height, which is 10. Added 2, and the next bit is green. This is another triangle, which is a half, and it's 2 again, times 10. And then the next bit is I add, and the next final bit is black, and it's going to be a half, and this here is 2, but now do you see this height is minus 10? Can you see how that gives me a negative displacement automatically? I could look and I could use intuition or conceptual understanding and say that this triangle that's underneath the axis is a negative displacement. Effectively the force has reversed direction. But I can also just get it by being careful about my graph. It's positive 10, it's negative 10. So my work is equal to 10 added to 20 added to, well, let's have a look at this. This is going to be a half to 10. That's going to be 10 added to minus 10. So work is equal to, that cancels with that, 30 joules. 30 joules is not up here. Shame on me. It should be plus 30 joules. My object that the force is acted on has overall, in this first 8 meters of displacement, an increase in its mechanical energy. So there we go. Let's look at the next slide. This next slide is a bit more complicated. It says an applied force F is related to displacement by a relationship. It's a inverse square relationship, a bit like gravity. if we have the Earth as we go higher in altitude, as we get further away, so our gravity falls off, and if we double the distance we get 1/4 the gravitational field strength. If we triple the distance we get 1/9 the gravitational field strength, because it's an inverse square. Okay, I've tried to show that by showing a relatively large force when I'm close to the Earth, and a relatively small Earth when I'm a force when I'm further from the Earth, from the mass that's causing this effect. Where force is in newtons and the displacement is in meters. What is the work done by the force for a displacement from 2 to 8 meters? Okay, so I can say the work done is equal to the integral of fx dx. So the work done is equal to the integral of 6 over x squared dx. Let's write that down in a more convenient form. It's equal to the integral of 6x to the minus 2 dx. And I know that the integral is going to be equal to, increase the power by 1, put it in the denominator, so it's going to be minus 6 over x. There's my integration, and basically I need to have my limits, and my limits are between 8 and 2, so this would equal, it's going to be minus 6 over 8 minus 6 over 2. So my work is equal to, well, it's going to be minus 6 over 8 minus 24 over 8, which equals minus 6 over 8 plus, minus and minus make plus, 24 over 8, which equals 18 over 8, which equals 2, leaving 2 over, 2.25 joules, positive 2.25 joules. So initially we had a big force, so a big force moving through a set distance will do a lot of work, and as we get further away we have a little force moving through the set distance which does less work. So most of your work is done down here, and as you get further up it's less and less work has been done per meter of displacement. So there we have it.